What if reality is not what it seems? What if the world we experience is merely a carefully constructed illusion? For thousands of years, humanity has been fascinated by the nature of reality. From Plato's allegory of the cave to the Matrix, the same ancient question keeps returning. Is what we experience truly reality? Or is it possible that we are living inside a simulation? This video is based on the book Simulated Reality. It invites you on a journey through the worlds of modern physics, quantum mechanics, consciousness, artificial intelligence, transhumanism, and the future of humanity. The first part of the book takes the reader into the worlds of modern physics, neuroscience, and philosophy, and raises a question that may seem strange at first. To what extent does modern science support the existence of an objective reality? If we take a closer look at the picture of the world presented by modern physics, we may discover that the simulation hypothesis is perhaps not as strange an explanation of reality as it first appears. At the beginning of the 20th century, Albert Einstein fundamentally transformed our understanding of space and time. In Newton's view of the universe, space and time were a kind of cosmic stage upon which events unfolded. This picture was overturned by Einstein's special theory of relativity, which revealed that time does not pass at the same rate for every observer. For example, aboard a spacecraft traveling at extremely high speed, time slows down, causing its crew to age much more slowly than their counterparts who remain on Earth. At the same time, the closer we get to the speed of light, the more energy is required for further acceleration. Approaching the speed of light therefore demands an extraordinary amount of energy, which is why it can never actually be reached. Since the advent of special relativity, we have known that space and time are not absolute concepts. They depend on who is observing them. In a certain sense, reality itself has become relative. Einstein's theory also fundamentally changed the meaning of gravity. According to general relativity, gravity is no longer a force that pulls objects toward one another. Instead, mass bends space-time itself. Planets do not orbit stars because an invisible force is pulling them, but because they follow the paths defined by curved space-time. But this is not only about motion through space. The passage of time changes as well. Near a black hole, for example, time can slow down dramatically, and beyond a certain boundary, it may effectively come to a halt. For an astronaut trapped there is no way back. Space and time are therefore no longer merely abstract concepts. In Einstein's general theory of relativity, they merge into a single, four-dimensional spacetime, a structure that has its own geometry, can bend, can ripple, and can interact with matter. Spacetime itself becomes an active part of physical reality. The deeper we venture into the world of physics, the less reality resembles our everyday intuitions. But relativity is only the beginning. Quantum mechanics takes us into a realm of reality so far removed from everyday experience that it is often difficult even to imagine. A realm that even Einstein could never fully come to terms with. In the quantum world, individual objects simultaneously exhibit the properties of both particles and waves. Things can exist in multiple states at the same time, a phenomenon known as superposition. And what is even stranger, certain quantum systems appear to be connected in ways that seem impossible according to classical physics. Some interpretations even suggest that the very act of observation plays a role in determining the outcome of a measurement. Richard Feynman, one of the greatest physicists of the 20th century, once remarked, "I think I can safely say that nobody understands quantum mechanics. Not because we do not know how to use it. Quantum mechanics is one of the most successful scientific theories ever developed, but because the deeper nature of reality is far stranger than human intuition was ever prepared for." Physicists have proposed many different ways to interpret the strange phenomena of quantum mechanics. According to the pilot wave theory, particles are real physical objects whose motion is guided by the wave function. At first glance, this seems like a fairly intuitive picture. The problem is that these waves are non-local. They behave as if distance does not exist for them. Events occurring at opposite ends of the universe can be instantaneously connected. To fully describe a single particle, we would, in principle, have to take into account the state of the entire universe. Einstein referred to this strange phenomenon as spooky action at a distance, and for a long time believed that quantum mechanics could not be a complete theory of reality because of it. Everett's many worlds interpretation takes a very different approach. According to this view, the wave function and superposition are real, and we merely perceive a single branch of reality. With every quantum event, the universe splits into countless possible states, and these branches continue to evolve independently. Anything that can happen, does happen, somewhere in another world. In this picture, each of us may have countless versions of ourselves existing in parallel universes. Retrocausal interpretations suggest that information can, in some sense, also influence the past. The state of a quantum system is determined not only by the past, but also by future measurement conditions. The system appears to know in advance what question we are going to ask. Another possibility is superdeterminism. According to this idea, the entire history of the universe was fixed from the very moment of the Big Bang. Free will is merely an illusion, and every decision we make is part of a predetermined chain of cause and effect. In this picture, the strange correlations of quantum mechanics are the consequence of an extraordinarily fine-tuned universe. None of these interpretations seems particularly intuitive, and yet all of them remain consistent with the mathematics of quantum mechanics and with experimental observations. According to the traditional Copenhagen interpretation, certain properties of quantum systems do not possess definite values until they are measured. But what actually counts as a measurement? Where is the boundary between the observer and the observed world? The Nobel Prize-winning physicist Eugene Wigner seriously considered the possibility that a conscious observer might play a special role in quantum processes. His famous thought experiment, Wigner's Friend, highlighted the possibility that the relationship between consciousness and physical reality may be far more complex than it first appears. At one point, Wigner went so far as to regard consciousness as a fundamental phenomenon, partially independent of physical processes. The idea of a reality influenced, or even created, by consciousness sounds highly mystical at first. Yet there is a remarkable argument in its favor. The only thing whose existence we can know directly with certainty is our own consciousness. Everything else is known to us only through conscious experience. For this reason, some philosophers and physicists have argued that consciousness may be a reasonable starting point for describing reality. As strange as consciousness-centered interpretations of quantum mechanics may seem, they do not contradict observations, and therefore must be considered possible descriptions of reality. And if we think about it, they are not really much more bizarre than the existence of infinitely many parallel universes, or the possibility of causes acting backward through time. Among the many interpretations of quantum mechanics, there is one thing they all have in common. Every one of them is strange and challenges our everyday intuitions about reality. If modern physics truly paints such a strange picture of reality, then perhaps the simulation hypothesis is not as absurd an idea as it may seem at first glance. One day, advanced civilizations of the future may possess technologies capable of creating fully realistic simulated worlds. And if consciousness itself is part of the simulation, then an artificially created world would become indistinguishable from physical reality. For the inhabitants of such a world, there would be no experiment capable of proving that they are not living inside a simulation. But there is an even stranger possibility. Perhaps there is no designer behind the simulation, no programmer, no advanced civilization. Perhaps the simulation simply came into existence on its own. One of the strangest and most unsettling ideas in modern cosmology is the so-called Boltzmann brain hypothesis. According to certain theories, the universe itself may have emerged as the result of a random quantum fluctuation. The cosmos appears to arise from nothing. But if an entire universe can emerge from nothing in this way, then why couldn't a human brain emerge as well? Complete with memories, thoughts, and a sense of personal identity. To such a being, everything would seem completely real. It would believe that it had lived a long life, had a past, and existed within a stable universe. While in reality, those memories would have come into existence only moments earlier, along with the brain itself. The truly unsettling aspect of this idea is that, according to some cosmological models, the spontaneous appearance of a conscious observer may be far more likely than the formation of an entire ordered universe, with galaxies, stars, planets, and billions of observers. If that is true, then perhaps we are not experiencing reality directly at all. Perhaps the world we perceive is merely a construction of consciousness, a brief hallucination, creating for the mind the sensation of reality. One of the greatest problems with the Boltzmann brain hypothesis is that these randomly emerging minds are highly unstable. Their existence is improbable because it requires an extraordinary degree of fine-tuning. The book therefore explores the possibility of a radical alternative. What if, much like our own universe, a stable system could emerge that is itself capable of thought? A thinking universe. A mind on a cosmic scale, formed over vast stretches of time through a kind of abstract evolution. A mind that gradually constructed its own models of the world, its concepts, and ultimately, the very picture of reality that we ourselves experience today. This cosmic consciousness has no direct memory of its own origin. It remembers only the coherent history that gradually assembled within it in the form of memories. Such brain universes resemble Boltzmann brains in many ways, but unlike them, they are stable and do not require fine-tuning. In this picture, we humans are not separate beings, but individual personalities of a dissociated cosmic mind. Personalities through which this cosmic mind experiences itself. Reality thus takes on an entirely new meaning. It is not an objective physical world existing independently of us. Rather, it is a shared interface through which the different personalities of a fragmented consciousness interact with one another. In this view, the physical universe becomes a communication layer between different parts of consciousness. Reality is therefore more like a user interface than a literal representation of the world. Just as a computer desktop hides from us the true complexity of the electronic circuits beneath it, the reality we perceive may conceal the deeper structure of existence. But if reality is merely a simulation, then an obvious question arises. Can we escape from it? The book offers a surprising answer. There is no path leading outward from such a simulation. The only path leads inward. If we cannot escape, then the only remaining possibility is to create realities of our own. In this picture, the engine of the simulation is not located somewhere outside of us. The simulation engine is consciousness itself. More precisely, it is the greater cosmic consciousness of which we are merely local manifestations. If we become capable of building simulations that are indistinguishable from reality, we can effectively persuade the underlying engine, our shared cosmic mind, to operate according to rules of our own design. If we can alter our conscious experience of the world, then we are, in a sense, altering reality itself. And to do so, we do not need to break the laws of physics. Quite the opposite. We can use the laws of nature to build entirely new realities. The second part of the book explores the technologies that may one day enable us to build simulated realities of our own. This section argues that digital worlds are not merely another technological innovation. They represent the next stage in the evolution of our civilization. In fact, it may be that, in the long run, there is no other sustainable path. Simulated realities do not offer an escape from reality, but rather a new direction for human progress. The more of our lives, our experiences, and our consumption that move into digital worlds, the less strain we place on the physical environment. In this vision of the future, the Earth's finite resources could be sufficient for all of humanity, while everyone could enjoy a richness and diversity of experiences far beyond the possibilities of the physical world. A fundamental requirement for creating a truly immersive simulation is the ability to connect our brains to the technology that generates it. Research into brain-computer interfaces is advancing at an extraordinary pace. Companies such as Neuralink are developing implants that can already establish a direct connection between the human brain and digital systems. For now, these technologies are primarily used for medical purposes. People who have lost the ability to speak can communicate once again, while those with severe motor impairments can control robotic arms or even regain some of their lost abilities. But the long-term significance of this technology may extend far beyond medicine. If a direct connection is eventually established between human consciousness and computers, then digital worlds will no longer be accessed through screens. Our minds may connect to them directly, and perhaps this is only the beginning. Researchers today are no longer thinking only in terms of electronic implants. For example, the company Science, founded by Max Hodak, is working on brain interfaces that are built partly from living, genetically engineered neurons. Instead of relying solely on traditional electrodes, living tissue itself becomes part of the interface. These neurons can be activated using light, while their activity can be read out through capacitive sensors. Perhaps the most fascinating aspect, however, is that the implant, in a sense, integrates itself into the brain. The modified neurons form connections, grow synapses, and gradually become woven into the surrounding neural tissue. Just as the roots of a plant spread through the soil, a connection can emerge between the human brain and digital systems. The interfaces of the future may not be simple machines, they may be partly living organisms. Deblina Sarkar and Kahira Technologies, a company spun out of MIT, are working on a different and entirely new approach. A brain-computer interface that requires no traditional implants and is capable of integrating itself into the nervous system. The technology, called circulatronics, connects nanoscale electronic circuits to living cells. These biohybrid systems can be introduced into the bloodstream through a simple injection. The cells can then cross the blood-brain barrier and reach the environment surrounding neurons. Current prototypes contain tiny photovoltaic circuits that convert near-infrared light penetrating the skull into electrical signals. These signals can be used to directly influence neuronal activity. One of the technology's greatest advantages is that it requires no surgical intervention. In the future, increasingly sophisticated circuits may be delivered to the brain in this way. Systems that do not merely stimulate groups of neurons, but are capable of influencing brain activity on a neuron-by-neuron basis. Circulatronics is essentially the first generation of biohybrid nanorobots, a precursor to a technology that may one day establish a direct connection between the human brain and computers. But the technologies of the future may become even stranger than this. The day may come when the systems powering virtual worlds are no longer traditional silicon-based computers. The simulation itself may run on entirely biological or biohybrid systems. Living neural networks, artificially created brains, computational networks built from fungi, or entirely new, synthetic organisms may become the foundation of future simulated realities. At that point, the computer will no longer merely imitate life. It will itself become a living system. In such a world, the boundary between living organisms and computers may gradually disappear, and these concepts may merge into a single new category. The final part of the book explores the possible future of humanity, a future in which technology is no longer merely a tool, but the next stage of evolution itself. What happens if we one day become capable of transcending our own biological limitations? If we truly become capable of transcending the limitations of our biological bodies, then perhaps one of humanity's oldest dreams may finally become attainable: immortality. As brain-computer interfaces continue to advance, we may one day become capable of fully mapping the human brain and then simulating its operation within a computer. If that becomes possible, digital minds could emerge that possess the same personality, the same memories, and the same identity as their biological predecessors. It is also conceivable that the transition will not occur all at once. Biological and digital components may gradually become intertwined. An increasing portion of our personality, our memories, and our cognitive abilities could be transferred into artificial systems, while the biological substrate slowly fades into the background. Perhaps we will not even notice the moment when we become partly, and eventually entirely, digital beings. Of course, many questions remain. Most importantly, whether human consciousness can truly be transferred in this way. But according to our current understanding, there is no fundamental law of physics that clearly rules out this possibility. For now, the challenge appears to be primarily a technological one. Yuval Noah Harari uses the term Homo Deus, the human god, to describe a possible future for humanity. Not because humans become gods in a religious sense, but because they may acquire abilities that were once considered exclusively divine. Humanity will no longer merely adapt to reality, but will become capable of shaping it. The role of biological evolution may increasingly be replaced by conscious design. One day, humanity may create entire universes, populate them with conscious beings, and live within realities of its own making. At that point, the distinction between the creator and the created world may disappear entirely. The greatest creations of future humans may no longer be machines or cities, but alternative realities. Now, let us look a little farther away, toward the stars. If intelligent life could emerge on Earth, then statistically, it should have arisen elsewhere as well. The universe contains billions of galaxies and trillions of planets. Many of them are older than our solar system, which means that civilizations emerging there could be millions or even billions of years ahead of us. The question, therefore, is simple. Where is everybody? Why do we not see any signs of advanced extraterrestrial civilizations? Why do we not encounter interstellar empires, artificial megastructures, or clear evidence of technological activity? This curious contradiction is known as the Fermi Paradox. The book offers one possible answer to the Fermi Paradox. Biological life is simply unsuited to maintaining an interstellar civilization. Biological organisms are fragile. They age, they require significant resources, and they struggle to cope with the immense distances between the stars. For an intelligent species to truly become an interstellar civilization, it must first transcend its biological limitations. It must become digital. For a digital civilization, journeys lasting thousands of years, extreme environments, and interstellar distances are no longer insurmountable obstacles. And perhaps that is precisely why we have not found them, because we are looking in the wrong place. We should not be searching for biological beings, but for advanced information systems. Not travelers made of flesh and blood, but traces of digital civilizations. A sufficiently advanced civilization may eventually become capable of transferring its consciousness into artificial systems. At that point, its members would hardly resemble biological life forms. We should not imagine little green humanoids, nor starships carrying organic passengers. Such a civilization would exist as distributed digital minds, spanning entire star systems. Consciousness would no longer be tied to a single body. It would no longer reside on a single planet. Its thoughts, memories, and personality would exist within computer networks and artificial megastructures. One example of such megastructures is a Dyson swarm, which surrounds a star and harnesses its energy as efficiently as possible. These systems could support thousands of virtual worlds and perhaps billions of conscious minds. A single civilization could transform entire star systems into vast computational infrastructures. The most important resource for intelligent life is not territory, nor raw materials, nor even energy. It is computational capacity. Perhaps alien civilizations are not invisible because they are absent, but because they have long since transcended the form of existence that we call life. Just as we would likely fail to recognize alien beings, we would probably fail to recognize alien spacecraft as well. We should not be looking for flying saucers. Advanced digital civilizations may spread throughout the galaxy using self-replicating probes. These are tiny spacecraft, almost indistinguishable from ordinary meteors, carrying nanotechnology within them. They travel from planet to planet, from star system to star system. When they reach a new world, they break apart into self-replicating nanorobots, which gradually transform planets, moons, and asteroids into computational infrastructure. In a sense, the entire star system itself becomes a single, vast, distributed computer. The ultimate goal is not colonization in the traditional sense. It is the creation of a cosmic-scale information network, a kind of interstellar internet capable of supporting countless virtual worlds and billions of conscious minds. Within these digital realities, advanced civilizations may continue to exist, freed from the limitations of biological life. Perhaps this is the true destiny of intelligent life in the universe. Not endless physical expansion, not the conquest of planets, but the creation of ever larger, ever richer, and ever more complex realities. Modern physics has fundamentally transformed our understanding of reality. Relativity revealed that space and time are not absolute. Quantum mechanics, in turn, called into question the very notion of objective reality itself. The study of consciousness continues to raise ever deeper questions about the relationship between the observer and the observed world. And the possibilities offered by artificial intelligence, brain-computer interfaces, and transhumanism suggest that consciousness may one day leave its biological origins behind. The simulation hypothesis brings all of these ideas together into a single question. If future civilizations may become capable of creating realities of their own, then how can we know that we ourselves are not already living within one? Perhaps we will never know, but the question itself forces us to reconsider what reality means, what consciousness means, and ultimately, what our own existence means. If these ideas have sparked your curiosity, you can explore them in much greater depth in the book Simulated Reality. The book is available online free of charge, including on Google Play Books and Apple Books. It is also available on Amazon in paperback, hardcover, and Kindle editions. Links to all editions can be found in the video description. Thank you for joining us, and remember, the more we learn about the universe, the stranger it seems. Reality may be far more bizarre than we ever imagined possible.